yesterday we computed all the exponents in Ginsberg Landau theory. Okay, and basically the idea is very simple. You just look at this effective action, it looks like d to the dx, and there's this stiffness term plus something which I will start calling m squared, and then there's that plus dot dot dot, but then we didn't really need the dot 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 to do anything that we could do. Okay? What is it that we could do? So we figured out the specific heat exponent is supposed to go like T minus Tc to the power minus alpha 0. Then of course beta, so the magnetization is supposed to go like Tc minus T to the beta. Figured out beta is half, right? Then we figured out d by dh of this guy at h equal to 0 is supposed to go like T minus 2c to the minus gamma. That's called the susceptibility exponent. That's 1. Then if you take phi of x, phi of 0, that correlation function, if you're not at the critical point, it should go like e to the minus r over some correlation length and some powers. So let me put some powers here. R to the d minus 2 plus eta is r is actually the separation between the 2 points. Okay. This correlation length is supposed to diverge as t minus tc to the power minus nu. That defines the exponent nu. This is what is called the anomalous exponent of the field, the anomalous dimensional. Okay. So those are your critical exponents. One more. At Tc, you have phi goes like h to the 1 over delta, and for us, delta is 3. Okay? Good. So now, the question is this correct? And the answer experimentally is it is not correct. Okay? In 3 dimensions, it's not correct. So there's something inside the theory itself that tells you when it should fail. Okay? And that guy, that thing is known as the Ginsberg criteria. So the basic idea is very simple. There's a couple of subtleties, but the basic idea is to look at the fluctuations of the total magnetization in a correlation volume. Okay? And then demand that those fluctuations are smaller than the average magnetization. Okay, that's the whole idea of this. Okay, so let me define for you something which I will call phi L of 0. Okay, so this is something where I will take some volume which is of the order of the correlation volume. What's a correlation volume? Correlation volume is a volume which is like a d-dimensional thing with sides of the order of the correlation line. Okay? That's the correlation volume. But let me define for an arbitrary L here. So I'm going to define it as follows. Let's take the integral of d to the dx e to the minus x squared over L squared. Okay? Times phi of x. Okay? So, of course, I could have a sharp cutoff, right? I could create a disk or a sphere of the correlation volume, but that will lead to unnecessary ringing in momentum space. Okay, if you cut off something very sharply in real space, it has oscillations in momentum space, and you don't want that. Okay, so I'm cutting it off smoothly. Okay? Good. So now what I'm going to do is I'm going to take this to be C, all right? And that is the correlation. Good? So this is the total field value. I've added up everything. It's not an average because I haven't divided by anything. Okay? Total field value in this correlation volume. Now what I want to demand, the Ginsberg criterion says, I want the average of this to be much, much less than this squared. Okay, why do I want this? Let's ask. Okay, what's the point of this? What's the physics of this? Okay, so remember the correlation length tells you that every spin within this correlation length is correlated to another spin within this spin, roughly. Okay, that's what it tells you. So if I go very far away, if I go several correlation lengths away, then those spins over there will not know anything about my spin here, right? That's what the correlation length means. Good. So this volume is the right volume to look at for the average of the order parameter. Okay, this phi is the order parameter. Good. Now I can certainly compute the average of this guy very simply. Okay, and just take the average of it. This average goes like t minus tc or tc minus t to the beta. Right? I know exactly what it is. And this is just some integral. Right? There's some pi's and so on. Okay, from now on, I'm going to stop worrying about pi's. Okay? So if I take the average of this guy, it's going to be of the order of c to the d times tc minus t to the beta. You agree with that? Squared. No, that's it. That's just the average of the magnetization of the correlation volume. Okay? Now you see, this sort of really tells me how close I am to the critical point. Right? The closer I get to the critical point, the smaller this will get, like that.
Sorry,
yeah.
This average thing you were defining by taking the average of the integrand basically of the phi basically.
The Weight factor is exponential of minus y.
This is, so the statistically varying field is phi.
So you take the expectation of that.
Right. So, but when I take the square, of course there will be two integrals there. I'll have to take some correlation function.
So what if this equation is saying is that the variance should be very less than the mean basically?
So let me finish the thought. So the point is that this guy tells you how close you are to the critical point, okay? But this, suppose this was not true. Suppose I had the opposite. Then what would happen? There would be some correlation volumes where this thing would be very large, right? Much larger than the average square. So it would appear that that volume is actually much further into the ordered region. And there will be some other region where this might actually be zero if the fluctuations of this are much larger than the average square. So it will look as though the system is very inhomogeneous. Right? So it looks like it's deep in the ordered phase here, it's not at all in the ordered phase over there. That can't happen. If there's a single critical point, right, everywhere it should be magnetized uniformly. Right? So that is why this criterion is a very physical criterion. Okay? That's the motivation, that's the physical reasoning behind this.
So this averaging that you wanted, that is the statistical average.
That's the statistical average, absolutely.
Yeah.
I'm going to use this weight. Actually, I'm going to drop this, but okay. So that's what I'm going to use. All right? Good? So this part, very easy to compute, the right-hand side. What about the left-hand side? The left-hand side says, if I take psi c squared of 0, this will basically integral d to x, sorry, not d2, d to the dx, d to the, or let me call it x1, d to the dx2, right? E to the minus x1 squared plus x2 squared over c squared times the average of right? You guys agree with that? Okay, I've just written down two such integrals. That's fine.
Sir, that part when I was confused that why that e to the power minus x squared by beta squared that comes in the
Yeah.
phi.
What about it?
I didn't understand that why is it coming?
Oh, why is it coming? Because remember, I want to take the magnetization of a correlation volume. Okay? Now I could actually take a sphere, a d-dimensional sphere, and just cut it out of the bulk and add up all the phi's over there.
Okay.
But that's not a good idea because eventually I'm going to do something in k-space. And in k-space there will be some bad oscillations if I cut things out in real space, sharply. So I'm taking something which smoothly cuts it off.
Yes, in the case space also it will just decay.
Exactly, so and I like that, because I don't want to have any
Hmm.
bad properties in case space. That's why I did that. But this should be seen as morally equivalent to taking a sphere
Hmm.
of radius c and just averaging it.
Okay.
Okay, or adding up all the fields. Okay, it should be the same. Okay, good. Now this, we already know, depends only on the difference of the two coordinates. It depends on x1 minus x2. It cannot depend on x1 plus x2. So I can do the integral over x1 plus x2. Right? So, how do I do that? I'll just make a change of variables. I'll define capital X as x1 plus x2 over 2, that's the sort of mass coordinate, and the little x will be x1 minus x2. And then you know that x1 squared plus x2 squared is 2 times capital X squared plus little x squared over 2. Okay? Just do it out from this. Okay? Good. So you put that in there, and then the right hand side becomes part of. So I'm going to do the, okay, so let me write it out. So there's a d to the dx, capital X, d to the minus times capital X squared over c squared, right? This integral is just, I can do it. The result of this integration up to some factors of pi is going to be that. Okay? I can do the factors of pi if you're really interested, but it's not important. Then there is this d to the d little x, right? And then there will be this e to the minus little x squared over 2c squared. And then there's this quantity here. Right? So this quantity is, now I can call it phi of little x, phi of 0. Very good? Okay? Now what is this guy? So if I ignore the lambda, I can do it without ignoring lambda as well, but let me do it the simple way. Let me ignore the lambda.